just off the visualizer now. Yeah, so this handout I gave you, this goes through, just wait for this to fire up. So at the end of my notes, the end of the chapter 2 that you have there. Oh my God. Lights, no lights. No. That's better. At the end of the notes, at the end of chapter 2, I said we're going to look at a couple of applications. And these are the kind of thing that you're asked about in the final problem in the first assignment, which is looking at these kind of, this first idea, looking at the closest approach between two lines described using vectors. Or another kind of application is getting the line of intersection between two non-parallel planes. Or a similar one, which I might show you as well now, is finding, say, the minimum distance from an arbitrary point to a certain plane. Okay, and just how we handle those kind of problems using the vector description. Okay, so these two, the closest distance between two lines and the line of intersection of two planes is described in this extra 2-page handout which I gave out last time. But I'll just go through it and just point out some important features of it, and also do the minimum distance from a point to a plane one as well. I think in your assignment, the one you have to do is find the closest distance between a line and a certain point off the line. Okay, so I'm not going to go through that one exactly, but it uses very similar principles to the idea of getting the minimum distance between two lines, or indeed getting the minimum distance from a point to a plane. Okay. So this is this first example, closest approach of two lines, L1 and L2. Okay. So just a quick sketch so we can picture some of the stuff we're talking about. Here's a couple of lines, L1, L2. Remember, the vector description we had of lines was, for each line, we have a reference point, which is position vector P. And the other line, say, would have a reference point Q. I'll stick with the notation from the handout. And then we have a direction vector V, which is a direction vector for line 1, and a direction vector W for line 2. These are vectors, V and W are vectors that point in the directions of line 1 and line 2, respectively. So the lines have vector equations . Well, L1 has the vector equation. The position vector R is P plus TV, and L2, use S. The position vector S is Q plus, let's see, got the parameter U, UW. Okay, so the vectors are underlined here, the scalars aren't. So R is representing here a generic position vector of a point along L1, and S is doing that job for L2. And we're now, okay, we'll kind of work under the assumption that the two lines don't intersect. When we look at the solution, we should be able to comment on the case where, sorry, no, I'm thinking intersections. No, we'll just go ahead with this. Sorry, the one special case would be, yeah, where they do intersect, or indeed if they are parallel. So if there wouldn't necessarily be a closest distance between. So somewhere in the diagram, there are 2 points. Let's draw them out here, which achieve the closest distance between them. Okay. So this will be one particular value of R here and one particular value of S. You know, when I'm talking here, I'm kind of identifying points in their position vectors. To speak absolutely correctly, I should be saying the point with position vector R, the point with position vector S all the time, but it's a bit of a drain and it kind of slows us down. So as appropriate, we kind of think of points and position vectors as being synonymous, okay? But we must always remember that they're not, that they are two different things. Okay, so we need to obtain this R and this S, okay? So here's a couple of ways that we go about it. There's a couple of different principles we can use. First of all, we'll be talking in terms of this vector R minus S, okay? So the vector R minus S will be the vector which points from S up to R. So it'll be this vector here. So that's just the difference of R and S. They're two expressions we have from the vector equations of the lines. So that would be Q minus P plus UW minus TV. I'll just package Q and P together. That will make some of the algebra that's coming slightly easier. Now we're looking for when the distance is minimal. Okay, so when this distance is minimal, so we need to get an expression for the distance. Well, it's actually easiest to work with the distance squared. Remember, for any vector x, its modulus squared is equal to the dot product of the vector with itself. And that's how we're going to deal with, because we've got all these vectors here, so we'll get to the distance by taking the dot product with itself. And rather than sticking a kind of big square root sign over everything, we'll just work with the distance squared, okay? We're also using this idea, you know, the minimum square distance is achieved at the same place as the minimum distance. So we just want to find out when and where the distance is minimized, but that's the same thing as saying when and where is the square of the distance minimized. Okay? The minimal square distance is just the square of the minimal distance. So I'll just step down a bit. So the norm squared of R minus S will just be the dot product of the right-hand side with itself. So when you take the dot product of the first bracketed vector Q minus P with Q minus P, you just get the norm squared of Q minus P. And then you take the dot product of the middle vector with itself, and that will give you U squared times the norm squared of W. Then you take the dot product of the third vector with itself, and that gives you T squared times the norm of W, the norm of V squared. So those are the three individual vectors squared, and then you got to, sorry, the dot products with themselves, and then you got to think about the cross dot products. Okay, and remember the dot product is commutative. So the two that are taken in the different order, you can package them together. So we'll have twice the dot product of Q minus P with W, and the scalar U in front of W, I'll just move out here to the front. So it's 2U Q minus P dot W. And then it's minus 2T q minus p dot v. And then finally, we have the kind of cross term dot product between these two. And again, that's going to have a minus sign attached to it because one of these is minus, the other one is plus. So that's minus 2 times ut v with w, the dot product of v with w. Of course, if you're dealing with any particular problem, you're dealing with any given two lines, you have to think that, you know, a lot of these things here are specified. So if you have all the information about lines 1 and line 2, that means you know exactly what the vectors p and q are, and you know exactly what the vectors w and v are. So they would be known to you in this problem. So this long expression that we have here, you see, we know exactly what this is. You'll be able to evaluate this. The w squared, the norm v squared, all these dot products you'll be able to actually evaluate. Okay. The parameters in here are the u and the t. So they're the undetermined as yet multiples of the direction vectors on each line that gets you to the points r and s. Okay, so it's just the u and t that are unknown to us in this. Okay. So we can think of this, we can name this as delta squared. It's the square of this minimum distance, and it's a function, well, it's a function of all the vectors, q, p, v, and w in the general case, but assuming that those are given, it's a function of the parameters u and t. And we've just started looking at functions of 2 or more variables in the maths methods, and we will get on to dealing rigorously and systematically with the notion of minimum points and maximum points and so on, stationary points of functions of 2 variables. But for now, we can use the principle is that, well, it's clear from the geometry that there won't be any maximum distance between the 2 lines, right? You've got these 2 lines which aren't the same and which aren't parallel. I mean, the maximum distance between the 2 lines, you know, if you're choosing one point on one line and another point on the other, well, you can just send the points off in completely opposite directions, and so you can achieve whatever large distance you want. So there is no maximum distance. So that means any kind of stationary value will be a minimum value, where the 2 points on the where the points on the 2 lines make their closest possible approach to one another. So the only stationary point that could possibly arise here would be a minimum. Okay. So using that, we can say that the minimum will be achieved. The minimum delta squared, and hence the minimum delta, the minimum distance, is achieved when the partial derivative of delta squared with respect to u is equal to the partial derivative of delta squared with respect to t, and when they're both 0. So this minimum distance will be achieved when these 2 partial derivatives are both 0. And we can take the partial derivatives readily enough. I mean, the way these things depend on, the way this big long expression depends on u and v is not that complicated. You've either got a u on its own, or a t on its own, or you maybe have a u squared, a t squared, or a u times t. So the dependence on u and t just goes up to order 2. So there's no barrier there to obtaining these partial derivatives. And in terms of working out the partial derivatives, all the other quantities are just constants. So all these other vector quantities, the norm squared or these dot products, they're just treated as fixed quantities because they're not varying with u and t. U and t, remember, are the varying multiples of the direction vector used to move along the line. Okay. So we can write down these partial derivatives. Delta squared d delta squared du Well, the first term here, this norm of q minus p squared, that doesn't depend on u. The second term does. You've got a u squared there. So its derivative is going to be 2u norm of w squared. The third term, the t squared v squared, where we're differentiating with respect to u, so we treat any other variables around as if they were constants. So that t squared is just treated like a constant. So as far as the differentiating by u operation is concerned, this whole thing is just a constant. So it has a derivative of 0. So it doesn't appear. Here we've got 2 times u times this dot product. Okay. So its derivative will just be the thing that's multiplying u. So 2 q minus p dot w. There's no u in this one. So that has a derivative 0. And there is a u in this one. It's multiplied by t times this dot product times 2. So its derivative will be minus 2 t v dot w. Is that okay? Should I clarify anything there or explain anything there for you? Everybody happy with how that came out? Okay. So differentiating this expression with respect to u. The other parameter t gets treated as a constant when you're differentiating with respect to u. And indeed, all the other vector quantities, or the norm squareds, or the dot products, they don't depend on u and t, so they're treated as fixed quantities as well. So this is, as far as differentiating with respect to u is concerned, this is a constant, so it goes 0. That thing is something u squared, so it's 2u times the something. The other thing is a constant, so it won't appear. This thing is u times a constant, so we get the constant. The other thing doesn't have a u, so it goes to 0. And this has a u, it's just some constant times u. So we write down just the constant, the minus 2t v dot w part. And similarly, to get the derivative with respect to t, just do the same operation, this time focusing on t. And the first thing that comes up is the 2t norm of v squared. Remember, these norm squareds are just standing for the dot product of the vector with itself. Just maybe a slightly quicker way of writing it. So we're differentiating with respect to t. The next thing that comes up is this here, minus 2 times q minus p dot v. And then we get the minus 2u v dot w. And of course, we're looking for the stationary point. We're looking for the minimum point. So as we've said, we're looking for when these two equations are simultaneously 0. Now that is a type of problem which you are well equipped to solve. It's just a system of two equations in the two unknowns u and t. And the way u and t are appearing there, I'll just put a little, I don't want to underline it because they're not vectors. I'll just circle the two parameters, t and u. Okay, it looks complicated, but really it's just something times u plus a constant plus something times t. That's the first equation. Second equation is something times t plus a constant plus something times u. So they're just two linear equations in u and t. Okay, so we have the theoretical approach of a Gaussian elimination for solving those. So we can make use of that. And if you're dealing with two given lines, then all these things will be, you'll be able to evaluate them. So you'll know the vector w, you'll know the vector v, and you'll know the vectors q and p. So you'll be able to work out all these dot products and this norm squared. Okay. So the procedure then would just be solve this system. So solve these for u and t. And once you know u and t, you then know everything there is to know about r minus s. So you know the minimum distance there, okay? Because you just take that value of u and t and bring it back up here, and put it into the r minus s, and you'll be able to work out what that minimum distance is. And indeed, you'll be able to locate the 2 points, r and s, that achieve that minimum distance, because you'll know the position vector of r and the position vector of s. Because if you know the information about the lines, you know p, v, q, and w here, so you'll be able to determine r and s once you know u and t. Yeah, any question? There is a different, yeah, so what's your different way? Yeah. Yeah, so there's another way as well, which you can use and determine, hang on a sec, determine minimal. And this way won't be, as lengthy as it looks if you're given the information at the start about the vectors, because all these equations will look far simpler. But yeah, the other way of getting at it is, so when you mentioned dot products and so on, well, it goes back to this. So what I've written there at the end is just solve these for u and t and determine the minimal distance r minus s, which is that minimum distance you're looking for. The other way you can do it kind of without engaging with the calculus is to use this principle, which I guess is what you're talking about. So there's the r and s. And what remark do you need to make about Jason, is it? What remark do you need to make about these two, the situation to get started with that? Well, so the thing that kind of does the equivalent work of the calculus is, what's the principle here that you use to get started? Yeah, and what about that normal? Yeah, so the point is that this minimal distance line is perpendicular to the two lines. That's the point. Is that the minimum distance is always achieved along perpendicular. Okay. So if you think about it, so this minimum distance vector perpendicular to L1 and L2. Why is that true? I mean, maybe the minimum distance line hits one of the lines at a bit of a slant. So you could think, why? Well, suppose it was the case that your R was up here and the S was down here, and let's say that was still a right angle, but let's say this angle here, theta, and theta was not equal to pi over 2. I mean, what can you kind of say? Well, can you see a shorter distance between the two lines there? Well, if you draw the line from R to L2, which does make a right angle, then you've got a right angled triangle there, with this angle theta being not equal to pi over 2. So you've got a right angled triangle, so that means this other side must be shorter than the side r minus s, because the side r minus s is the hypotenuse of this triangle. Okay. So these minimum distance lines must always be perpendicular to the two lines, because otherwise, if they weren't, there would be a shorter distance there, okay? Because you can form a triangle for which this is the hypotenuse. So you could say the existence of this triangle call this S prime. The existence of the triangle RS S prime shows that the distance R minus S is not minimal. So using that principle, yeah, so then you can start talking about the normal vectors to the two lines or that. Or, well, another way to start with it is to take the expression we had for R minus S on the previous page, which was, remember, Q minus P plus WU minus TV. Well, if R minus S is perpendicular to L1 and L2, that implies that if you take the dot product with R minus S with the two direction vectors, then you must get 0 in both cases. Okay, because saying they're perpendicular to the lines is saying that they're perpendicular to the direction vectors of those lines. But this is where this method kind of joins up with the other one, because when you work out these two, quantities, so working out these two equations. So again, you still have that the U and the T are unknown. So the U and the T are in here in this R minus S, so they're still unknown at this stage. You're still trying to determine those locations on the two lines. When you hit R minus S with W and V and look at the equation that comes out, so working out these two equations gives us the equations, well, the ones we just worked out, the d delta squared du and the d delta squared dt again. Gives us the equations for this again. Although they may have been multiplied by, for the equations before, actually I should have said that the equations we had before had these 2's in them, so you can cancel out the 2's. I think you just get the previous equations we had without the common factor of 2 on the one side. So you still get thrown into this situation where you've got the two linear equations for U and T, which you then go ahead and solve. Yeah, it's an alternative principle that can get you to those two equations. Okay, so I think you'll find that stuff, and if you understand that, I think you'll find that useful in tackling, I think, the final assignment problem about finding the minimum distance from a given point to a line. I'll just quickly show you, yes, I did the quick review of the LaTeX earlier, so I'll just quickly show you how you get started on the problem of minimum distance of a point to a plane, and it's quite similar. So this is another application, minimum distance from point to plane. So think of a plane P and a point A. And then there's some point A prime. So the point A prime in P is closest to the point A. Got the origin off somewhere here in the picture. So if you're given the information about the plane and the point A, basically the problem is, how do you find the point A prime? And once you know A and A prime, you can evaluate the distance between. Well, remember, the info that you have at the start, you have the point P, you have the plane P described somehow. The plane P is described via its normal vector, and this vector equation here, n dot r equals some fixed value, alpha, say. Now the picture is kind of suggesting the main principle. For very similar reasons, as in the case of two lines, this minimum distance is always achieved along right angles to the plane. Okay. So the info you have is here, and let's say we also have the info A, the position vector of the point A, which would be some position vector little a. So the principle you would use to get this principle is that the vector A prime is perpendicular to the plane P. So if we let A dash be the position vector of this other point, that means that A minus A dash so vector A minus A dash, which is the vector which the displacement vector from the point A down to the point A prime, that must, because that's hitting the plane at right angles, that must be a vector parallel to the normal vector n. So this must be some multiple of n. So the task now becomes find lambda. So we want to find lambda. And we can do it, we can find lambda by taking the dot product of that. The dot product of that equation, take the dot product of both sides with n. Because then you get an equation when you expand out the dot product, you get n dot a minus n dot a prime equals lambda n dot n. And we're searching for lambda, but we get this equation for lambda, but actually we know everything else, okay? Because if the plane P has been specified and the point A, which we're looking for the minimum distance from the point A to the plane, has been specified, then we know the normal vector. We know the position vector little a. We know the dot product of the normal vector with itself. Do we know n dot a prime? Well, we don't know a prime yet, because we're looking to find this point on the plane which is closest. But we do know the quantity n dot a prime, because a prime lies on the plane. So the vector little a prime must satisfy this vector equation of the plane. So that n dot a prime in the equation down below is just alpha. So this quantity here is alpha. So it's a minus alpha in there. And this is known. And this is known as well. So everything is known apart from lambda, so you can get the value of lambda from that. You just divide across by the n dot n. And you just evaluate everything. And then you know lambda. Then you know lambda. And then you know that this minimum distance vector is just lambda times n. So if you know lambda and you know n, then you'll know the magnitude of lambda times n. So we determine lambda from this, and hence this, which is the minimum distance. Minimum distance of A to P, point A to the plane P.